So let's have another look at this idea of geometric representation. So looking at it, thinking of it as geometry rather than algebra. So briefly mentioned this the other day when we defined modulus and argument. But we can represent complex numbers not only as a point on the Argand diagram, but as a vector. So there's our Argand diagram. There's our complex number z equals x plus iy as a point. And there's only one spot I can put it as a point, and that's, well, right there. But if I represent it as a vector, so the red line there, the advantage is I can translate it. So I can slide it wherever I like. And it maintains the same properties. So, look, I could move it down there. Oh, I could move it over there. I can put it anywhere I like. Right. So it does not matter where I place it. The length does not change, and the angle that it's making with the horizontal axis there doesn't change. So when I say I can move it, I'm just talking about sliding. But if you want to work out the point, all you ever do is you say, well, what's the head of the vector minus what's the tail of the vector? Do that subtraction and it'll tell you what complex number it's representing. So when it's joined up to the origin, the point and the vector sort of land in the same spot because you're going, oh, x plus iy, the head, minus the tail, which is 0. So you get the same number. So then if we're looking at it as a vector rather than a number, how do we add them? How do we subtract them? So again, there's Z1, represented by the point Z1, but also the vector. In this case, I've anchored it to the origin, so it is the same point it ends up at. And there's another one, Z2, and I want to add these together. Basically, you slide one of the vectors and join it to the other one. So you're adding it to the other one. And you just join them head to tail. So if I get the blue one, slide it up there, place the tail on the head of Z1, and where it ends up there, which is Z1 plus Z2. So it's the point Z1 plus Z2, but if I was to draw in the line there, it's the green vector that I've drawn. So that's how we can add them. And the nice thing is it does not matter because A plus B should be the same as B plus A. Now I just slid the blue one onto the red one, but if I was to slide the red one onto the blue one, I end up in exactly the same spot because essentially I've got a parallelogram there. And opposite sides are equal and parallel, so I must end up at the same spot. So the diagonal of that parallelogram is Z1 plus Z2, but the interesting thing is the other diagonal would be Z1 minus Z2. Head minus tail. Or it could be Z2 minus Z1 depending on which end you make the head and which end you make the tail. Okay? So to subtract, we can place the vectors head to head rather than head to tail. It's sort of like adding the negative vector. Okay? So if I was to slide the blue one onto the red one, but instead put the head on the head, I'd end up down here at Z1 minus Z2. Which would be that black vector there, and if I was to slide that black vector, you'll notice it fits nicely between those two. So it is in fact the same vector. So again, whenever you want to work out what the vector is representing, head minus tail, and that'll tell you what it's representing. This brings up an interesting little result we can prove very easily with a simple fact we know about triangles, and I suppose a simpler way of saying this, although it's not that this is very complicated, it says any triangle in a side will be shorter than the sum of the other two sides. But a simpler way of thinking about that is the shortest distance between any 2 points is a straight line. So if you go straight between the points, so one side of a triangle, that's always going to be quicker than going off to a third point and then going back up to the other one, which if you think about it, that's what a triangle is. So in any triangle ABC, and geez, it would have been really good if I labelled up there A, B and C. Just pretend A, B and C are labelled. You can pick any of those triangles you wish. Then the length of AC would be less than or equal to the length of AB plus length of BC. Equality would happen if AC was a straight line, because then B would be on AC, so the lengths would be identical. Now, it has the advantage then, was we can interpret this with complex numbers then, because remember we said the third side of a triangle, well, let's say I'm doing the one which has the green vector, the blue vector, and the red vector there. The green vector, the length of it would be modulus of z1 plus z2, so it must be less than or equal to the sum of the other two. So it's a nice quick way of proving that the modulus of z1 plus z2 will always be less than or equal to the modulus of z1 plus the modulus of z2. Okay, all right. So again, just going over addition again. A point A is z1, point B is z2, and as we just saw, the diagonal then would be z1 plus z2. Subtraction. So the vector negative z1, so if I was to slide z1, but instead of placing the tail at the origin, I place the head at the origin, that would become negative z1. There's that vector, but it fits nicely in the other diagonal when we go z2 minus z1. Okay, let's look at a question. It's quite an old one now, but it's a good one to demonstrate a lot of these things. So they gave this particular diagram, and so P and Q represented Z and W. Thus the length of PQ, so they even gave you that information that, oh, guess what, the vector joining P and Q would be Z minus W, head minus tail. So its length would be the modulus of Z minus W. Show that, the modulus of Z minus W. So basically it's that triangular inequality I was just talking about. So, well, to answer the question, I suppose, I can't just write it down and go, oh, it's true because it's true. It's got to put some sort of, logic behind it. So I say, oh, well, the length of OP we know is mod Z, the length of OQ we know is mod W. They told me the length of PQ is mod Z minus W. Well, using the triangular inequality, I can therefore say that particular result. Okay. They want us to now find R, which is Z plus W. So the first thing, we have to locate that point. But then they said, well, what can be said about the quadrilateral OPRQ? So now we want to add the two together. So I slide one, or create the parallelogram. Oops, I gave away the quadrilateral. And that blue vector, or R's the point, would be Z plus W. What can be said about the quadrilateral? Well, it's a parallelogram. But then they made it a little bit more interesting. They said, hey, but what happens if the modulus of Z minus W is the same as the modulus of Z plus W? What do you now know about W divided by Z? So you've got to interpret that with your diagram. What have you got? You've got a parallelogram. What is Z minus W? What is Z plus W? Well, they're the two diagonals. So we're now talking about a parallelogram whose diagonals are equal. Okay. So where does that get us in our family tree of quadrilaterals? Parallelogram, diagonals are equal. Parallelogram branches down to rhombus. It's not true in a rhombus though that they're equal. Rectangle would. That's probably the most general shape, isn't it, that we could have. So all right. So what can be said about W divided by Z? Well, if you have a look at your diagram, if I now know that's a rectangle, then the argument of W minus the argument of Z would become the vertex in the rectangle. Well, we know that's 90 degrees, or pi on 2. So I know the argument of W minus the argument of Z must be pi on 2. And then I can use my rules to play around with that and go, oh, hang on, argument of W minus argument of Z, that's the same as argument of W on Z. So the argument of W on Z is equal to pi on 2. What is that telling me about W on Z? It has to be purely imaginary. Because if its argument's pi on 2, it must lie on the vertical axis. So it's purely imaginary. In fact, it must be above 0 in the picture. Because if it was below, it'd be minus pi on 2, wouldn't it? So the way they positioned it, but I think that's probably good enough, just getting the purely imaginary, but I suppose technically it should be greater than 0, the y part be greater than 0. Okay, well, what about multiplication then? And we saw a bit of that idea before. Remember, we know, playing again with the rules, that the modulus of Z1, Z2 is same as mod Z1 times Z2, and when it came to the arguments, we add the arguments. So when we talk about the picture, okay, so if I go into r cis theta form, the argument of the new one is θ1 plus θ2, and that's where we get this idea of rotating the vector. We're adding on the argument of what we're multiplying by. So if you multiply Z1 plus Z2, Z1 will be rotated by the argument of Z2, so θ2. And the length then will be stretched by a factor of whatever the modulus is of R2. So let's have a look at this. There's Z1, and if I was to multiply by just cis theta here, so the length of the vector in this case does not change. Because you'll notice I'm multiplying by cis theta. Well, its modulus is 1, because it's like saying 1 cis theta. So the length of the vector hasn't changed, but its position's changed. I've rotated it theta, the argument of the thing I'm multiplying by. So that would be the position of Z1 cis theta. Now, had I multiplied it by r cis theta, then I would have rotated it into the same position, but then I would change the length by whatever that factor is. So if it was 2 cis theta, I'd double it. If it was a half cis theta, I'd halve it. It becomes a very important fact. If you multiply by I is, of course, cos pi on 2 plus I sine pi on 2. That's a rotation of 90 degrees. 90 degrees. And it would be anti-clockwise, of course, anti-clockwise. Okay, but always remember, if you're trying to work out what a vector is, head minus tail. So get the head, subtract the tail, that'll tell you the complex number you're talking about. Alright, so here's a little picture here. A, B, C, D placed in various positions. I didn't mention it, but I think that's a square. So, now, if I wanted to work out all of these points, I know D is 1 and I know A is omega. So the first one I'm going to work out is C. So how do I get C from what I know? Well, if I get this vector, they're both joined to D. So if I was to rotate about D, as I say, this is going to be a square. So if I was rotating 90 degrees, I would end up with vector DC. So I could write that as, well, the vector DC, now when you're writing vectors, so you notice the arrow notation for vector, remember it's head minus tail, so you write the tail first, then the head. So DC, D is the tail, C is the head. And it would be vector dA multiplied by I, so let's substitute in, well, what is dA? This is where you've got to be real careful. Common mistake here would be just to say, oh, well, it's omega times I, but it's not. It's not the point that's being rotated, it's the vector that's being rotated. So dA is actually omega minus 1. And my answer won't be the point C, my answer is the vector DC. So the answer is C, whatever C is, minus 1, head minus tail. But I should now be able to play around with that and make C the subject. And there it is in all its glory. I mean, we don't know what omega is, but if we did, we could sub it in and work out the actual number. So 1 minus I plus I omega. Some people might write it as the line above, because it sort of looks like you're saying real plus imaginary, but omega is a mixture of real and imaginary anyway, so. All right, well, let's work out B. Well, B, if I was to now slide this new vector that I know and join it onto the point A, so to the point A, I'm adding the vector DC. I'm sliding that along and joining it. So again, let's substitute in. So this time A is omega because I'm talking about the point, not the vector. So I would substitute in omega for A, but the vector DC, remember that was C minus 1, but we know C minus 1 is omega minus 1 times I from what we did before, and we can play around with that, and I've just left it like that. So minus I plus 1 plus I omega would be the B. That's one way I could do it. There's another way I could do it, of course. Because another way I could get B is I could look at the point C and slide the vector dA. Should give me the same answer. So the point C, which we worked out over there, is 1 minus I plus I omega. And to that, I'm going to add the vector dA. So head minus tail, omega minus 1. And if I play around with that, sure enough, I do end up with the same answer. But of course, there's another way I could do it. See, to work out B, imagine the vector dB. Well, it's anchored at D, so I could rotate my vector dA to the. Now, I know it's a square, so therefore I'm rotating 45 degrees, or pi and 4. So that's why I've multiplied it by cis pi and 4. But the length of the vector will change. It'll change by a factor of root 2. Well, how do I know that? Well, think about a square, chop it in half, and you're going to have your classic 45-degree triangle. Sides are in the ratio 1, 1, root 2. So the hypotenuse, which would be dB, its length has been stretched by root 2. So I've also multiplied it by root 2. Now this should, as I say, theoretically, it should work. So let's see how we go. So dB, well that's b minus 1, because I'm talking about the vector, not the point, is equal to the square root of 2 times cos pi and 4, I sine pi and 4, times dA, which is, there it is, omega minus 1. Cos pi and 4 and sine pi and 4, of course, is 1 on root 2. So that'll cancel with the root 2. And I get 1 plus I times omega minus 1, and then I've moved the 1 from the other side over. If I manipulate this, I should end up with the same one. So expand out, and sure enough, there we go, we get the same answer. I guess it just depends on how you're thinking about it at the time. You know, you'll look at it and see it one way, you might look at it and see it another way a different time, but they should all work. I mean, otherwise we're in trouble because maths has to work. 2001, this time they gave a rectangle, and we're told OC is twice the length of OA, and A is omega. First question, well, what's C? What's C? So how do I get to C? The only thing I know at the moment is A. They're both joined to O, those two vectors, so I think I'll do it via rotation. They told me it's a rectangle, so I know it's a rotation of 90 degrees. And rotation of 90 degrees is multiplication by I, but they've also told me the length is twice as big. So I'm going to multiply by 2I. So I've changed the length as well. Now, OC, well that's nice, it's joined to the origin, so that will be the same as the point C. And OA is just omega, so there's C. 2I times omega. Part 2. What complex number corresponds to the point of intersection D of the two diagonals OB and AC? Okay. Well, I know the diagonals will bisect. I think that's the key. Knowing that gives me a nice quick way of doing it, because if they bisect, then all I have to do is find the midpoint of either OB. That'd be a bit silly because I don't know what B is at the moment. But it would also be the midpoint of AC, and I do now know both of those points. So that's probably going to be the quickest way of doing it. So D will be the midpoint of AC. So it's the point AC, because it's the midpoint, not the mid-vector, the midpoint, although in this case the point and the vector is the same. But, so it's A plus C divided by 2. So it's omega plus 2I omega divided by 2. Well, tidy that up a bit. A half plus I times omega. Let's say, I don't think I did bother doing it this way, but the other way you could do it is work out the coordinates of B and then find the midpoint of OB. That should work out as well. What else could you do? You could rotate the vector. Ooh, that's nice. Just realised. You could rotate the vector OA 45 degrees. Oh no, it wouldn't be 45 degrees. It's not a square. But we could work out the angle because we know the sides are 1, 2. And, oh, that's starting to sound messy, isn't it? But theoretically, it's a way it could be done. Okay. So we have an equilateral triangle length of 1 unit. OBCD is a square. Find the complex numbers represented by B, D and C. Now, when I read a question like this, I think that's interesting. Why did they say B, D and C rather than saying B, C and D? I figure they're probably giving me a hint here. Find D before we find C. There must be some reason they wrote it that way. So all right, let's find B. They've told me that's an equilateral triangle. So the coordinate they've given me is the point A. Because they told me the length of the equilateral triangle is 1. And A is sitting on the real axis. So A must be 1. I'm going to get 1, but this time, because it's an equilateral triangle, I'm going to rotate it 60 degrees, pi and 3. So it'll be 1 times cis pi and 3, so cis pi and 3, which is a half plus root 3 on 2i. So I have B. Now they're giving me the clue, let's find D. Yeah, because now I could get B and rotate it 90 degrees, or I could go back to A and rotate it, what would it be, 150 degrees, wouldn't it? Either way. So what did I do? I got the new point, B, and I'm going to rotate it 90. So IB, just multiply that by I, so it becomes minus root 3 on 2 plus a half I. Okay, let's find C. What's C? Oh yes, I can now slide that vector up. So the point C will end up being when I get the point B, but add onto it the vector OD. So I'll get a half plus root 3 2i plus minus root 3. Well, I didn't say it had to look pretty, did I? There it is. So 1 minus root 3 on 2 plus 1 plus root 3 on 2i would be C. A, B correspond to complex numbers. Both of those triangles are your classic right angle isosceles. So that's an important bit of information. We know things like sides are in the ratio 1 root 2. The angle would be 45 degrees, things like that. Explain why. Oh, I know how you love these questions. And you have to explain yourself rather than do the maths. Explain why P corresponds to the complex number 1 plus I times Z1. Well, hey, doing maths is an explanation anyway. I'm a bit like you too. If I can do maths, I'll do maths. So here's my explanation. The vector AP would be the vector AO, but I'd be multiplying it by minus I, because notice the rotation is clockwise rather than anti-clockwise. So it'd be a rotation of minus I. Subbing in, P minus A will equal minus I, O minus A. A is Z1. Rearranging all that, and yes, we get what they're looking for. 1 plus I, Z1. Okay, part 2, which is missing. That's interesting. I just labelled it part 2. It says part 3. Let M be the midpoint of PQ. What complex number corresponds to M? I'm tipping the missing part 2 would be to find the coordinates of Q. Because it seems a logical thing we have to do. So all right, let's do the same sort of thing. QB will be BO times I. Subbing in, and we get 1 minus I Z2. We want the midpoint, not the mid vector. So it'll just be P plus Q on 2. Add them together. I suppose that really is good enough for an answer, but it's not underlined, so I probably did something with it, did I? No, yeah. Doesn't really matter. Same thing. Okay. So some out of Cambridge, but also the Terry Lee exercise in this one's not too bad either. So I photocopied that one for you to have a go at there.